Moving on into episode 9, this time it's about the 6502 CPU. We'll look at some resources, then we'll create a small circuit and monitor a test program to see how it all works. Last episode we used a ROM chip to put a test image on the screen. Clearly, to be of any use we need to be able to change what we put on the screen, ideally changing it often, so we can play a game. You know what we need to make a picture? We need a CPU to put things into video memory. So this episode will take a break from the full game circuit we've been making to take a closer look at how the 6502 CPU operates. We'll build up a test circuit on its own so we can concentrate on just that part, and then we'll chuck in a ROM and monitor the address lines and data lines with an Arduino, and then we'll build up the same circuit in Verilog to see how the FPGA side works. It's going to be good fun. The 6502 CPU is an 8-bit microprocessor that was designed by a team led by Chuck Peddle for MOS Technology. The 6502 was designed by many of the same engineers that had designed the Motorola 6800 microprocessor family. Peddle saw that these CPUs were too expensive and envisioned a cheaper, reduced instruction set CPU. Motorola's Semiconductor Products Division management was overwhelmed with problems and showed no interest in Peddle's low-cost microprocessor proposal. A team formed at MOS Technology to create this new CPU. There was actually a 6501 chip that could fit into the same socket as the 6800 chip, and the 6502 that wasn't compatible, the difference being an internal clock module on the 6502. Due to the similarity of the 6501 and 6800 chips, Motorola successfully sued MOS Technology, and it was agreed to drop the 6501 chip. Commodore later acquired MOS Technology, but the 6502 chip had licensing agreements to allow other manufacturers to produce the chip. One such version is the 65C02, the CMOS version by Western Design Center, with its low power consumption, high possible clock speed and some new instructions. This version is still produced and sold today, and so it's the version we'll be using in our design. The 6502 CPU is used in many home computers and consoles. The list includes the Acorn Atom, Electron and BBC computers, the Apple I and II computers, the Atari 2600, 5200 and 7800 consoles, an Atari 800 computer, Atari Lynx handheld, the Commodore PET VIC-20, C64 and C128 computers, the Oric Atmos, the Famicom and the NES consoles, and the TurboGrafx 16 console. I'd like to take a quick look at some resources for 6502 learning and programming before we dive in. The first is the Ben Eater channel on YouTube. Ben starts off from zero and teaches you everything you need to know with a lot of great ideas for CPU breadboard building, including how to use an Arduino to act as a slow monitor of the CPU and watch the address and data lines to see what's going on. In addition, the clock and debounce circuits based on the 555 chip that we're going to see in this episode were first shown in Ben's video series. I can't recommend that series enough, it really is very excellent. Next up are some resources based around the Apple I computer. The Apple I offers a nice simple architecture to help understand how the 6502 chip gets put together with RAM and ROM and peripherals to make a full system. The site Apple Fritter has a good book called Apple I Replica Creation. The book describes how the system works and also offers good grounding on electronics and logic, but also software such as BASIC and assembly language that makes the system run. It's free to view the whole book on the site, or you can pay a small fee for the PDF version. I'd really recommend it since you can learn a lot. If you look at that book and you want to make MiSTer cores using the 6502 CPU, obviously what we're doing on this channel, a good help is the Apple I core that has been developed for the MiSTer. It's in Verilog and I've used it to study the CPU, RAM and ROM modules as a background to what I've been doing on my project. No doubt it's really useful, so I'd really recommend taking a look at the code for this one. Next up, we've got resources for learning about programming in machine code on the 6502. We'll get into the instructions or opcodes that the 6502 uses to carry out operations a bit later, but some great resources are 6502 Assembly Language Programming by Lance Leventhal. It's really the go-to standard for learning how to program the 6502 chip. You can find it free on the internet, and I'll be stepping through some of the test code to my project a bit later. Easy 6502 is a website tutorial that lets you learn and play with a virtual 6502 system, and compile 6502 assembly language and see how to operate with different kinds of addressing techniques, loops and jumps. All the good stuff. I personally think it's a really friendly way to learn 6502 there, so go and check it out for yourself. Finally, we've got an online 6502 assembler that converts the assembly language into actual opcodes the 6502 CPU recognizes. In theory, you could do this manually by hand, looking them up in tables, but nobody has done this since the early 80s, and it's really not a friendly thing to do. We'll be using this tool in a little while to create some test code. Here we have the breadboard with the 6502 CPU, the 2716 ROM and the 7404 NOT gate TTL chip. I'm using the Western Design Center 6502, so some slight pinout difference is there from the original 6502. I'm using the Western Design Center version since we can slow the clock speed right down to around 1 Hz and monitor the program executing much slower than the typical 1 MHz that it runs at in the arcade game. So on the 6502, first we're going to connect up power, that's 5 volts input on pin 8 where it says VCC, and then ground on pin 21 where it says VSS. Pin 1 is the vector pull on the newer 6502. It's an output that we're not really interested in, so we'll just leave it. Pin 2 is the ready pin, and we need that one high, so we connect that to the 5 volt rail. Pin 3 is Phi 1, which is an out of phase clock. We'll leave that since we don't need to worry about it. Pin 4 is the maskable interrupt. That is used typically for things like reading a controller. It can be turned on and off by software, and we're going to make it, we're going to tie it high because it is active low, and it will interrupt the program running if it's low. So we tie that high to 5 volts. Pin 5 is not connected. Pin 6 is a non-maskable interrupt, which is similar to the IRQ on pin 4, but that is not able to be turned off by software. Again, for this test we want to tie it high, so we'll connect that to 5 volts. Pin 7 is sync, and it's an output, and it gives us an indication of when an opcode is being fetched. We're not interested in that, so we will just leave it as it is. Pin 9 to 25 is, they're the address lines of 0 to 15, allowing the CPU to address 64K of ROM and or RAM. Pins 26 to 33 are the data lines, 0 to 7, and that allows 256 bits to be stored at each location of the address. Pin 34 is a read-write pin, and it tells us if the CPU wants to read or write from the RAM or ROM. Its high level, 5 volts, is a read, and its low level, 0 volts, is a write cycle. Pin 35 is not connected. Pin 36 is the bus enable, an input that takes control of the buses from the CPU. If set high, the CPU can use the address, data buses, and I/O registers. So we need that to be tied high to 5 volts. Pin 37 is the Phi 0 clock input. I'll be using an external clock circuit to trigger it a couple of times a second. Pin 38 is the set overflow. I've left it, but you can also connect it high to 5 volts. Pin 39 is the boosted version of the input clock, Phi 2. We don't typically need to use this for our kind of circuit, so that's just left. And pin 40 is a reset. It's active low, and so to reset the circuit we make it go from high to low. We're going to connect that to our reset circuit. So let's look at the memory map of the circuit we just saw, with the A15 address line connected via a NOT gate to the ROM enable pin. So that means we activate the ROM for any address above 32K or 8000 hex. The size of the ROM is 11 bits wide, so that's 2K in size. 2K is 800 in hex, or 000 to 7FF. So in memory above 32K, 8000 hex, we have that 2K repeated 16 times from the 8000 to FFFF, since we're not monitoring or controlling the bits in black, shown here. Our program only references ROM from F800 to FFFF region, so it's not an issue, but if we were referencing lower memory, we'd see a repeat of that same ROM information over and over and over again. So I've written a short routine to test out the CPU. I've put our test screen in ROM like we had it before, but I've put it in slightly different memory location because I want to put our program to read the screen at the lower part of the ROM. If we take a look at the program in assembler, that's what we're doing. First instruction is load the Y index register with the value 0. Then load the accumulator with the value in the location of FB00 with an offset of the Y register. Firstly, the offset is 0, so we load the value from ROM at location FB00. Next, we store that value into RAM at 0200 with an offset of Y. Again, Y is 0, so it's stored at 0200. Now the smart people will realize we don't have any RAM, so it's really not doing anything with it. But when we monitor the CPU actions later, we'll want to see a write cycle being triggered there, so that's why I put it in there, even if we can't actually do the writing. Next, we increment the Y index register to 1 higher. We compare the Y register to the value 1F. If the value of Y is 1F, then we break the program there. If it isn't equal to 1F, then we branch back to the label LL0, and that takes us back to load the accumulator instruction. This time we're loading the accumulator with the value FB00 plus 1, so FB01, and storing it in 0200 plus 1 or 0201. And so on until y does equal 1f. The 1f value signifies a whole line of data on the screen, so just a short demonstration we can look at later. To get the machine code from the assembly language, we open the Virtual 6502 assembler webpage. Copy and paste in the assembly code, or write it in directly into the box. Press Assemble. It should say Assembly OK, and put the object code in the right-hand box. This then needs to be copied into a hex file and written to the EEPROM. If we take a look at the hex file, we can see how it's organized for our test run. First, we make it double wide so it looks more like the screen, as we discussed in a previous episode, with 32 bytes per ROM visible. So down here we have our converted program data to read the screen memory up to 0C. From 1A0 we start the screen data, and that goes down to 45F. Now don't forget, this is a little misleading. Remember the memory map? The ROM goes from 000 to 7FF, but it will be sitting in the memory location of F800 to FFFF. Actually, we saw it 16 times in the upper 32K of ROM. So when we're looking at the hex file, we need to think about converting the location in our heads from 000 to F800, and so on for higher addresses. So the address of 1A0 in the hex file will be seen as F9A0 in the ROM file when we read it. And so in our program, that is reading info from location FB00, that is looking in our hex file at address 0300. And so it will read the whole line from 0300 to 031F. Now, one very important addition to the hex file at the end is what's called the reset vector. The reset vector is where the CPU looks when we run the reset sequence. In the case of the 6502, the reset vector is stored at location FFFC and FFFD. So on a reset, it reads those two locations and gets a memory location for where to start running code. You can see here we have 00 in FFFC and F8 in FFFD. The CPU is what is known as little endian, which means it reads numbers in the reverse way round to how we have them in decimal, i.e. lowest number first and highest number last. So 00F8 becomes F800 for the start address. If we don't put that in the top of the ROM, then it won't know where to go on the reset sequence. Okay, so we've got the hex file burned to the EEPROM and dropped back into the circuit. The circuit is connected up to the slow clock driver circuit and a debounced reset switch. The slow clock circuit uses a 555 timer chip to create a slow pulse that will drive the 6502 CPU. I'm using it as the Phi0 input on pin 37. The reset pin input of pin 40 is active low, so we need the switch circuit to stay low for at least 2 clock cycles to start the reset sequence. I'm using a 555 timer again to debounce the circuit, that is, to ensure we don't get continual on-off when we press the reset. Not so critical for the slow timer, but it will be important when we use it to reset the full speed version. The schematic for my circuit is shown here. I've got the circuit of the slow clock, the debounced reset, and then the circuit showing how the CPU is connected up to the 2716 ROM chip. This schematic is on the GitHub for reference also. In order to see this circuit is working properly, I'm going to use an Arduino to monitor the address lines and the data lines and the read-write pin of the CPU. This method is taken directly from the earlier mentioned Benita videos about 6502, and so I'd really recommend checking out his video for more information on the method. You can see that the yellow long wire is coming from the clock circuit at the top of the screen and goes into the CPU clock. The long blue wire is the reset and goes to the reset pin of the CPU. The address pins go from 52 down to 22 on the Arduino, pin 52 connects to A0 pin, and so on until pin 22 on the Arduino connects to the A15 pin of the CPU. Pins 53 to 39 connect to the CPU data pins of D0 to D7 in that order. Here are another few views of the Arduino connected to the breadboard. Importantly, the ground of the Arduino must also connect to the ground rail of the circuit. And then we have pin 2 of the Arduino connected to the Phi0 clock input, and pin 3 is connected to the read-write pin. With all that connected, we can load up the Arduino IDE and the program for monitoring the CPU. We need to upload the code to the Arduino, which will compile it and upload it to the device. We then need to open a console window to see the stream by going to Tools, Serial Monitor. When we turn on the board's power, we start getting info into the serial monitor. Now if I hold down the reset button, you can see that the data output stays the same a little while, and then when I release, it starts to go through the reset sequence of looking at FFFC and FFFD. The program runs by looking at the ROM file at the FP00 address for one line of the screen. We'll have a look at the results line by line to see if it's doing what it should right now. Okay, so on the screen here I've got the outputs that we saw earlier from the breadboard, the Arduino, and then I've got here just the code that we can talk through as it's executing. So the first thing to describe over here is what we actually see in this file. So this is the binary address line, this is the binary data line, this is the hexadecimal address line, and the hexadecimal data line. And then this here is telling us if there is a read or write cycle going on. So that's really useful as to what the CPU is trying to do. The next thing is, obviously you saw in the video that we held the reset down. We held the reset down when it happened to be F808, and so we have these cycles while we're holding the reset down. And then after that, when we lift the reset, because remember it is enable is active low, it goes into the reset sequence. So that typically, I'm not sure it's always the same, but effectively we're seeing here this FFFF, and then it goes through here. The important point is it then goes to the reset vector FFFC and FFFD. And you remember we saw in the hex file that was 00 and F8, which gives us the address of F800 for starting our program. So that's where it then starts picking up the program that we're going to execute. Now over here is the program we're going to execute, and I've just put over the top here what each data is against the address that it is, and it's also down here as well in terms of when we're looking at it. But just to show that, for example, on this line F800 has got A0 and 00, so that's F801. So it takes up an address as it goes through the different hex areas there in the ROM file. So first we want to show obviously that the data that we're getting reading the CPU is matching up with what we want from ROM. So obviously you can tell straight away if your program isn't working or your hardware isn't working, if it's not picking up the right data. So F800, it read A0. So that's correct. At that point, it is A0. F801, it read 00. That's fine. That's exactly what we want. F802, it was reading B9. Again, good. So we've got a system that we think's working. So that's fine. Now, if you've got issues with noise or whatever, sometimes you will see that it'll work a lot of the time, but intermittently maybe not, and it'll throw you off. So you do have to look at like the whole cycle. That's what we're going to do here. But it's so far so good. It's looking okay. So let's actually have a look at what it's doing. So F800, it's doing the load 0 into the Y register. So it says A0, which is load Y, load it with 00. So we're saying A0, 00, so that's fine. And then it says load A into the load A with the value that's in FB00 plus Y. So it's doing that here. B9 is the load accumulator with the 00FB. And it finds in FB, so now we've gone to FB, so that's really good as well. That means it's obviously following what we want. It's looked in the address there that's loaded, and it's found 00. So if we look at our hex file, let's remember that 300 is the FB00 in the ROM file. So all we're doing is we're loading, we're going through 300, which is FB00 in the ROM, and we're going through each one, loading it into the accumulator and then writing it out again. So we just need to monitor that we're getting the data value that we expect. So the first one is 00. Where are we? Down here, FB00. Yes, so we get 0 there. And then all we want to do is, it takes that in, and then 99 is store A into 0002. So 0002. And then it goes to 200 or 0200 hex. And the interesting thing here is it's actually doing a read cycle first at that RAM address, and then it writes it. I really don't know why it's doing that read cycle, and this is part of the reason why you need to see what a CPU does, because it'll do slightly curious things. And then when we're simulate that in Verilog, we need to understand if it's doing the same thing. If it's not, is it important? Sometimes it's not. We can pretty much disregard this, but it's interesting that it does that. So it does that read, then it writes 00 to the ROM. Now remember, it's not writing to anything, so if we wanted to read it back, we obviously wouldn't be able to read any data. But it's quite happy trying to write out to something that it can't write out to. So we've done that. Then we're F808, which is increment Y, which is the C8 opcode. So we got that, C8. C809 is the compare Y with 1F. So we got there compare Y. Now interestingly, that takes 2 cycles. So this is where programming a CPU is important, because some opcodes take 1 cycle, some take 2. And that's how you get efficient or non-efficient code. And with the 6502, there's something called a 0 page that we'll see in a couple of episodes time, which makes things a lot faster. The 0 page RAM, where you can do things in much smaller opcodes. So that's where that gets interesting. So we're comparing that to 1F, so that's that 1F there. And then it says D0 branch if not equal to F8. So branch if not equal to F8, F5, sorry, and then FD0, F80D is 00, so it's that one there. Now interestingly, if you were going to look at a basic code, you would say compare to 1F, Y to 1F. If it doesn't equal 1F, go straight back to 02, which is that bit there. Now interestingly, it actually looks at that line as well. So it goes to break here. I don't know why it does that particularly. It doesn't act on it, but it does look at that next bit. It loads it in. And then it goes back to 802. So again, another curiosity there of what it's doing in terms of actually operating. So when you're simulating a system like that, you need to know it's doing these things, it's operating like that. Okay, so that's the first cycle that it does. Obviously we've gone back to 802 and it just does all this again. So let's just look another couple of reading in. So if we go to our hex file, the first bit of useful data it reads into is 303, which is FB03. So if we try and find FB03 in here, FB03 is just there. So that's the first time we expect to read 10. So if we go back, yes, 10 is there. So it's reading that in write, and then it's writing that out to 0203, it's writing 10. So that's good, we're picking up the line that we should. The next one to go to that would be important would be 09, so C2 on 09, so we expect zeros here. Yeah, we've got 0 until we get to 09. That's 6, 7, 8, FB09, so that's C2. And then, yes, C2 there. And then we'll just look at one last one, 0B. So we've got 0B there. 0B is C4. And again, yep, C4 is what we expect there. So that's good. It's definitely reading what we need, and it's writing it out to a pretend RAM that it can't see. Now let's go to the end of the line. So let's find 1E. So if we go down to FB 1E, which will be down the bottom here, that's 1D. Where do we 1E? So we've got to 1E. And then again we are doing that, we look for a C8 on F808. F808 is increment Y, so if we're 1E and we add 1 to that, it's going to be 1F, and then we compare to 1F, and this time we are equal. So then what it does, FB says branch if not equal, so it's still reading those two, but we don't branch. We actually this time go F80D, which is that one, we break, and interestingly it creates it goes to the next line, which is also a 0, which we don't have in this code but in the hex, F80E, which is another 0. So again it's reading that one afterwards, which is slightly curious. After that we've basically broken the program, so whatever it does is kind of going to be either nonsense or a specific a routine. We can see here it does just break apart. It starts reading not necessarily garbage, but so FFFE, FFFF, we can see that happening quite often, and then the rest in between seems to be pretty much the same thing, but some addresses there are slightly odd. But in any case, you know, we've got what we want out of the program, so that's good. You know, we've managed in this episode to put together a CPU, put in some test code, monitor that test code with a really useful way of doing it with an Arduino that's done it nice and slowly. It gives us plenty of time to have a look at the address lines, the data lines, and the read-write cycles, compare that it's doing what it should be doing. We found out a few things about how opcodes are working, and a few things that the CPU does that's slightly odd and non-intuitive. So that's it for this episode. Next time we'll look at how we recreate the same system on the 6502 circuit in Verilog. So see you next time.